Hi chemistry students, today we're going to look at intermolecular forces. To begin, let's review what we've already talked about. So first, at the beginning of this particular unit, we looked at three different types of bonds. The first one is ionic, the second one was covalent, and the third one was metallic. Let's take a second and figure out what these three bonds are between. So if we look at the ionic bonds, we'll notice that they are between a metal and a nonmetal. And we'll also see that their electronegativities are extremely different. So we saw in some of our examples that maybe one is 3 times more electronegative than the other. So the nonmetal, if it was fluorine, would say be about 4.0, and the metal, if it were lithium, would be 1.0 for its electronegativities. So the difference between them would be 3.0, or fluorine would be 3 times more electronegative than the lithium. If we look at the covalent bond, in a covalent bond we have two nonmetals. And depending on if these bonds are polar or nonpolar, we could see anything from no difference in electronegativity all the way to a significant difference in electronegativity. Not as much as a 3 times larger electronegativity, but somewhere around maybe up to like a 1.7 or 1.9 electronegativity difference. In a metallic bond, you have many metal atoms that will be bonded together, and they basically take their small number of valence electrons and they will pull them all together, and they will allow them to travel between the atoms because these electrons will be delocalized. They won't be centered around one atom, and they also will form what we call a seat of electrons. Now these bonds happen between 2 or more atoms within a molecular compound, but what we want to look at today is how does a molecule interact with other molecules? So that's where intermolecular forces come into play. And so intermolecular forces are between molecules. So rather than talking about the bonds that make up that molecule, we now want to look at how the molecules interact between each other. So what are some of those forces that are inside? That are on the outside rather than the inside of the molecule. So what we have here are solids, liquids, and gases. And when we look at the state of matter, notice how the molecules here are extremely close together. So in a solid, these intermolecular forces would be rather strong because there would be a lot of connection between those molecules. So higher intermolecular forces, whereas in liquids they're a little bit further spaced out, so still quite a bit of intermolecular forces there, more interaction between those molecules. In gases, however, since they are so far apart, and you can see over here to the right, they really have no interaction with each other. Gases have very, very small intermolecular forces between them, and also we see that again it's because of their space between the molecules. So what are the types of intermolecular forces that are out there? Well, there's van der Waals forces, which are made up of dispersion forces, and we also have dipole-dipole forces. Then there's also what we call hydrogen bonding, which seems a little weird because it's not a true bond, but because hydrogen bonding is so strong, that intermolecular force is so strong, they just call it a hydrogen bonding, but it's not a type of bond. It is an intermolecular force. So let's look at van der Waals forces first. Van der Waals forces are weaker than covalent and ionic bonds, so they're a lot weaker. There are two types of van der Waals forces. We have dispersion forces, which we're going to talk about in detail, and then we have dipole-dipole interactions. Dispersion forces, which is the first type of van der Waals force that we're going to talk about, are caused when the electrons in polar or nonpolar molecules are temporarily off balance. This is going to cause them to have a slightly negative and a slightly positive end just for a few seconds until the electrons can get back balanced. So this is our weakest form of any kind of intermolecular force. It's the weakest of all of them. We have very small charges, and the attractions are very short lasting because you're only looking at when the electrons are off balance. If we look at the diagram here, I want you to notice that atom A here, its electrons have become centered around this side of the atom, so you can see I'm coloring it red here. This is where most of your electrons are lying within the electron cloud. And so if you remember, our electrons are traveling around in this electron cloud, and they're moving all between those, all within those energy levels and those orbitals. However, as they're moving around, sometimes they can get off balance. So where most of them will end up on one side of the atom versus the other. So that's how we get this small partial negative charge, and the other end that doesn't have many electrons will be a small partial positive charge. And when that happens, that can also cause atom B to be off-centered. So then atom B's electrons will become off balance, where you have a slightly negative end and a slightly positive end. Now, notice that you've got your positive and your negative ends that are close to each other. There will be a force of attraction that's going to pull those two together. It will be very, very small, and as soon as those electrons can get back balanced, where they are not on one side versus the other, then this intermolecular force will be gone. And it will continuously keep happening over time. From time to time, you'll see this off balance of electrons on atoms, and they will have this dispersion force attraction between two atoms. But again, it's very, very short-lived, because as soon as those electrons get back balanced, then they will not have that dispersion force between them. They won't have that attraction between them. So what type of atoms are more easily polarized? So how do we get this off-balance electrons? Well, atoms that are easily polarized, if their electrons are distorted in the atom or in a molecule. So this increases with greater number of electrons. So the more electrons, the more moving negative charges that you have, the more likely it is for them to be off balanced, and where they will mostly be on one side versus the other from time to time. Also, the electrons in the outer shells are the ones that will typically get off balance. And then also, because of you want the greater number of electrons, and those electrons in the outer shells are the ones that are easily polarized, the ones that are easily shifted to one side versus the other from time to time. Typically your atoms with larger molar mass, which will be the ones with the greatest number of electrons, are going to be the ones that have dispersion forces. So our very tiny ones, we see very minimal dispersion forces. Those electrons tend to be more balanced and can able to move around. We don't see those dispersion forces as often, but with those larger ones with so many moving electrons, a lot of times they will have slightly negative and slightly positive ends just for a short amount of time. And again, it's a very, very small, because those electrons are moving so much that they will get off balance. So you can see here, when we look at the electrons in helium, notice in this one that they're on opposite ends. So we've got an electron here, and we've got an electron on the other side, pretty evenly dispersed throughout that atom. But if we look at a helium atom number 2, notice that the electrons are all on this side, which is going to cause a slightly negative end and a slightly positive end. Because of that, that's going to cause the attraction to happen here because of that small atom. We can also see here in this picture that we've got an atom that has a slightly negative end where most of its electron density is happening on this side, and again over here we've got our slightly positive end. Notice that most of our electron density is away from the left side of the second atom right here, and so that positive and that negative will cause our dispersion forces. This is our dispersion force between those two. Now as soon as they get back balanced, no problem. You won't see that dispersion force anymore, but while they are off balance you will see them attracted to one another. Dipole-dipole interactions. We've seen bond dipoles when we were doing polar covalent bonds. So a dipole-dipole interaction occurs between polar covalent bonds in separate molecules. So if we look here at this bond between iodine and chlorine, we see that we have a polar covalent bond here. So now when we have another chlorine and iodine polar covalent bonded molecule, the positive end, which would be here, the iodine, will be attracted to the chlorine, the negative end of the other molecule. The same thing on the other side. This negative end, chlorine, on the first molecule will be attracted to the iodine, positive end, on the second molecule. You can also see that we see dipole-dipole interactions between molecules on either side. So if we were to stick another iodine and chlorine molecule here, we would have interactions here. If we were to have another molecule here of chlorine and iodine, we would have dipole interactions there. And so again, those interactions are happening because of the slightly positive and negative ends that are formed from the polar covalent bonds. So just as I said, the negative part of one molecule is attracted to the positive end of another molecule. And in a solid, because they are so close together, we can see over and over again interactions between, see, we would have an interaction here between the chlorine and the iodine sides of these molecules. Over and over again, repetitively, you would have a lot of dipole interactions. In a liquid, because they're not spaced as close together, we would not see as many. And in a gas, because those molecules would be so far apart, we wouldn't see a lot of them at all. The last one that we're going to talk about is the hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force. It's a special type of dipole-dipole interaction in which hydrogen is directly bonded to either nitrogen, oxygen, or fluorine. We call that NOF. So a good way to remember that is just NOF. So hydrogen bonding is between NOF, nitrogen, oxygens, or fluorines. So when we look at water molecules, you'll notice that the slightly negative end here of the oxygen will be attracted to this positive end of hydrogen. And again, this interaction happening between the hydrogen and the oxygen, part of that NOF, this will be our hydrogen bond. You can notice here at some of the molecules, this is ammonia here, this is one right here, NH3, and hydrogen bonding is happening between the H's and the end here in the center. This would be a hydrogen bond here. We could have hydrogen bonds between two different molecules. So here's another hydrogen bond between ammonia and hydrogen fluoride. We have hydrogen bonding that happens between water, hydrogen bonding between ammonia and water happening here. Another hydrogen bond here, and finally another hydrogen bond here. Hydrogen bonding gives properties, some of its very, very unique properties, which will get discussed in class. But because of that hydrogen bonding, we have higher boiling points. It takes a while for it to boil. You can see some of the surface tension, so you can actually get water to do a few things, like when you drop water on a penny, you can get it to bubble over, or if you've ever put water into a cup and you've seen kind of a bubble over top of the rim, that's coming from its hydrogen bonding. So there's a lot of very unique properties about water that happen because of its intermolecular forces. So why are we talking about these interactions or these intermolecular forces between atoms and molecules? Well, intermolecular forces give the molecules some properties. And so looking at intermolecular forces, the more intermolecular forces that you have, the more attractions between those molecules. And so if you are trying to get them to go from one state of matter to another, it's going to take you more energy to break those intermolecular forces and get those molecules to change from a solid to a liquid to a gas. So we're going to look at higher boiling and higher melting points for things with stronger intermolecular forces, such as the example earlier when I was talking about water. Water, it takes so long for it to boil, and it takes a while for it to actually freeze for it to actually boil and it to actually melt because of intermolecular forces and those strong hydrogen bonds. When you have fewer intermolecular forces, there's less attraction between those molecules, and so we don't need as much energy to break them. So lower boiling points and lower melting points, because we don't have to go through breaking all of those attractions between those molecules. They will easily change from one state of matter to another, so lower boiling points and lower melting points. If you look at some of these organic compounds, such as methane, ethane, propane, butane, etc., as we look at these formulas, so CH4 would be CH4 would be C with the hydrogens bonded like this, whereas ethane would be C here with the 6 hydrogens bonded to it, and the lines represent the hydrogens. Notice that we have longer chains here, and so the more or the longer the chains, notice the higher boiling point, and that's because you have higher molecular forces. You're going to have more intermolecular forces that are going to be between the molecules. And so you'll be looking at this a little bit later as we go into more with intermolecular forces, but again, if you look at these longer chains, you've got more space for you've got more areas for you to have more dispersion forces that are happening. So more dispersion forces or more off balance of electrons that can happen with a longer chain. The more intermolecular forces that you have, the more intermolecular forces, the higher the boiling and the melting points. So you can see as you go down, notice how the boiling point continues to go up, and these long chains, like you see here with decane, notice it has the highest boiling point because, again, you'd have the most dispersion forces or the more intermolecular forces that are there. Because of that, you're going to have the highest melting and boiling points with decane versus your short ones like methane, who have very, very low boiling points and very low melting points as well. So just to recap, intermolecular forces happen between molecules. So IMFs are forces that are of attraction. between atoms or molecules. Bonds that we've been talking about, ionic, covalent, and metallic, are going to be inside. Those are bonding between atoms that are inside of a molecule. IMFs are forces of attraction between, so these are on the outside, so between atoms or molecules. Now there is practice on the back of your notes that I'd like for you to try tonight and see if you've actually mastered the material that was talked about in the video. If you're having a hard time with some of the pictures or being able to identify the different types of intermolecular forces, please feel free to go back through the video and see what those forces are again. Maybe some of the pictures or some of the discussion that we've just had on the video will help you to answer those questions. And again, have those questions completed when you come to class tomorrow. And I will see you later.